Okay, so let's solve for the final temperature. What you do is break the triangle down into what it represents. Final minus the initial. Just do that. Write the triangle T out into its longer expression. Okay? And then add the positive TI to both sides. I know what you're doing. Okay. Okay, it's okay. The TI cancels out and you get that's it. Okay, now we're going to put numbers to it. Let's take a look at page 167 in your workbook. I'm going to go over that with you. I'll go over that practice problem and the questions. I'll go over the sample and the practice problems with you. This is page 167, example or sample. Do that. Okay, just read the top of the page, 167. I would make a list. Go ahead. I'm just kidding you. Go ahead. Anytime. Yeah. Okay, I'm going to make a list. It says, top of page 167, 25 kilojoules. So that's, if there's any mention of joules, that's a form of energy. Okay? We're going to convert it to wait till he gets back. We're going to convert it to joules. Remember, converting kilometers to meters, there's 1,000 meters in every kilometer. So you solve for joules in a similar fashion. There's 1,000 joules for every kilojoule. I wrote down the conversion factor, 1,000 in red. So that works out to be 25,000 joules. We need to, again, stick with the units that are consistent with what you were given for the heat capacity. Joules, not kilojoules. Okay, so I'm making a list. This is what you do. Look at the unit if you're not clear. It says 50 kilograms, that's mass. It says water is initially what? It gives you a unit of degrees Celsius. That's your temperature, and it says it's initially, so that's your initial. Question is, what is the final? That's what I'm solving for. So that's why I had you solve for the final up here. We already got the expression. You need to be able to solve for the final and also the initial in some cases. So make sure you practice that. You know what to expect. Should look like that. Now all I have to do, once you solve for it, like we've already done, is plug in the values. You've got the list. Okay? Now, notice it says here, this is water. Water is either going to be given to you in the problem, it isn't in this one, or it's given to you in a table. So if we looked up water, I already mentioned it to you, it's 4,200. So I'll plug that in here. The C is 4,200. Plus the initial 20. Okay, so that's how they got their 20.1. I would round, in this case, maybe stick to 3 sig figs. You may need that extra digit. So again, really maybe one of the only things that may throw you off is finding the C value. That's, again, either in a table or it's given to you. I would memorize the value for water. It's so common. We use it so often. 4,200. I'm going to do some of the practice problems. Same page. Number 1, just read that to yourself. I'll go over it with you. Okay, it doesn't give you the C value. You'll have a table. In this case, I'm referring back to the table. I actually know the value again for water. It's 4,200. And it doesn't matter if you put Celsius or kilograms first in the denominator. Got everything you need. Just write down the equation. I put here positive to remind you we expect, because it's an increase in temperature. How do I know that? It says we're going from 18 to 80. We should expect a positive change in E. How are you getting an increase? You're adding energy, which is indicated by a positive change in energy. Now, how do I know that the 80 is the final? It says that we go from, those are your key words, from to something else. So whatever we go from is the initial. Whatever temperature we rise it to, that's your key word, to is your final. Okay, so this difference here, 80 minus 18, 62, that's a positive. It's not a negative change in or change in temperature. So that's going to give us what we expect, a positive change in energy. Which means just adding it to the object to increase the temperature. So this should work out to be 2.3. You can round to 2 or 3 sig figs. What's the unit? Yeah. If you're in doubt, the unit of any energy, kinetic potential, or in this case heat transfer is joules. Always joules. Okay, so see if you can do number 2. You've got everything. Just one point here. Let's just make a little. Your change in energy, we're assuming this is positive, is this. Okay, so mega stands for 10 to the ten to the 6. So you write it as a million joules. If it was giga, it'd be a billion, like the Tesla Gigafactory. Billions of joules as opposed to this millions of joules. Okay, so use that. Yes, it's positive. See if you can figure out the final temperature. You've got the. I already rearranged it for you, but see if you can rearrange it again. Do a little practice. See if you can get the same formula as I gave you for number 2. Okay. Yes, I gave you the formula. Let's see if you can derive it, because I'm not going to give you the derived form of the equation. You're not going to be given the figured out version of it. You have to figure it out. So let's see if you can do it. If you make a mistake, so what? But give it a try. And then compare it to what I already gave you. I'll make a list for you. It is water. They keep on repeating water. Again, you're going to be given a table or maybe the specific heat capacity given to you in the problem itself. In this case, we've got a table. I would, again, memorize it. It's 4,200. See if you can come up with that formula, because you're going to need to be able to derive it. Figure it out yourself. Just looking something up for you. Same equation as before. Solving for the final. Make sure you get those. This is a prefix, right? The big M, prefix. You see a big M, that means 10 to the, it's just a shorthand way of saying a million, 10 to the power of 6. If you see a giga, as in what the new Tesla factory is named after, that represents a billion, 10 to the 9. Yes, I'm a Tesla fan. Sorry. Okay. So final is equal to 1 million joules divided by M. In this case, M is 10. And the C for water, you're memorizing it. What is it? It's quite large. Yeah, water can absorb lots of heat before the temperature rises. So yes, it's 4,200. Memorize it. Plus the initial temperature in this case is 15. Okay. Okay. Now, we should get 39 degrees. Okay. That's if this is positive. So what gave it away for me? Just take a look at the question. We'll read it together. It says 1 megajoule is transferred to. That's what gave it away from me, as opposed to from. If the energy is transferred to, you're adding it, which means the energy should be positive. That's how I knew it should be positive, which meant that I should get an increase in temperature. Final temperature should be higher. If you saw the word, the heat is transferred from, then you would make that 1 million negative. You're removing energy. It's stuck in a fridge.
Mr. Reese told me to give you this.
Tell him thank you. I appreciate it. What is it?
It was like some Indian food. You're like.
I mean, I appreciate it. Thank you.
I was wondering why this guy like cooking his son. Fried pepper.
Try out 3. See if you can do 3.
Oh no, wait. I want to try that. Lucy said it was like, I think it's like Indian.
Read it carefully. I think you're tired.
How is it?
Okay. It's pretty good. That comes from a guy who's not picky. Not bad. Did you cook it?
Me?
Who cooked it?
No, it's like
From Bella? Or?
I think it's a restaurant. It's like they work for a restaurant and they just brought in food.
Oh, okay. Yeah, that's nice of him. Okay. So I'll make a list for you, and then I'll do it. Okay? Now, pay close attention. This is just a minor point you may miss. Because we're dealing with 12 grams, and look what follows after that number of water, the object we're referring to is the water to begin with when we're doing the calculation. The equation that includes the energy is referring to whatever the mass corresponds to. In this case, it's 12 kilograms of water. So we're talking about the change in energy. It's the change in energy of the water we're calculating, not the surroundings. So we'll deal with the surroundings in a second. Let's calculate what the change in energy is. And make sure you get the sign right. And you'll see why it changes later. Yeah? Yeah. Okay. Mass is 12. Specific heat is 4,200. You're going to be given that, or you just memorize it for water. It says here clearly in the problem that the water cools from, that's your initial, to 20 degrees. That's your final. That's how I knew to properly label it. It's the words that referred to it in advance, from and to. From means what you started with. Okay, so 2 means that's the final. It's 20. Started with 100. This whole thing, my point of saying all this is that the difference in the temperatures is going to be negative. So that is going to give me a negative answer. Okay? So let's do that. You end up getting a negative 4 million. Okay, now, be clear on something. The question, if we go back to it, is how much heat will be released to the environment? Okay? So, we didn't calculate the heat released to the environment. We calculated the heat, in this case, that was taken from the water. That's why it's negative. It's negative because we're talking about a decrease in temperature brought about because of the energy being sapped from or removed from the water. Where did it go? If the energy is removed from the water, it's got to go somewhere. It can't disappear. Where does it go? Yeah. Then don't let this confuse you. If we say it's negative because it's coming out of the water, it's positive when we're referring to the environment. If it's going into something, it's positive. So you would write down the energy that goes into the environment is positive 4 million. That's why if you look in the back, you check your answers, they give you a positive value. So we'll just write the energy transfer to the environment is positive. It's the exact same number. Is that Tibble, whatever. It's 1R, I think. Is opposite in sign. Yeah. Yeah. What? Positive. Okay. Correct. Now, have a read through this. I've got some handouts for you. I'm going to go through this with you, but this will. You already got it, right? Okay. So in this handout, you want to fix something where it says gigawatts. Gigawatt is not 10 to the 6. That's a megawatt. Giga is 10 to the power 9, 1 billion. Right here at the top, left hand or right hand corner here, it says power in watts. 1 kilowatt is 1,000 watts. 1 gigawatt is 10 to the power 9, not 6. Okay, so power, let's write that down. Okay, so power is just, it is energy, but it's the amount of energy that you're using per unit time. So the joules is on top, seconds on the bottom, which means the unit for power is joules per second. Okay, now we've gone one step further. You can use joules per second. There's nothing wrong with that. But we've gone one step further to abbreviate. It gets a little confusing because notice I'm writing the units in red. The unit that you'll see more often than joules per second is watts. W is short for watts. It's important that you distinguish it from this W here. This is work. Okay, that's why I separated the units from the variable with different colors. Let's see this. Okay. Efficiency. These are just definitions, so we need to know what the definitions are. It's defined as the output work divided by input work. Times 100%. Or okay, either one. Now, what do we mean by in and out? So I'm going to work with the power. I'm going to define this in terms of power, but it applies to work as well. The output is the useful power. What does that mean? That means apart from heat loss. Does not include heat loss. Okay? So keep in mind, this also represents work or energy. You could, instead of writing P out, you could write W out or energy out. It's the same basic idea. It's the amount of useful power, the amount of useful energy or work, which means what? There's no heat loss when we're calculating that. As opposed to what? The input power, input energy. Let me be clear on this. In refers to input, putting it in. No, don't get foul. Out refers to what are you outputting? Okay, so back to PN. PN, again, you could just replace the power with energy or work. It's the power that includes the heat. Due to what? Well, what generates heat in moving parts is friction. Due to friction or air resistance, some sort of resistance, but usually friction. So it's important you understand the difference. Output is the ideal, no heat loss. Input includes heat loss, or includes the amount of heat that's generated. So what does that mean? That means that the input is always greater than the output. Why? Because the input includes more. It includes heat, not just the useful energy. So, physical example of that. This would be the actual power you're getting out of the turning wheels or axle of a car. Actual horsepower. Of a car. What would this input power would be the power you get from burning the gasoline, which goes into obviously powering the car. No, sit down. You've been out already. The input is the energy you get from the gasoline. The energy you put into it per second. Well, where does that go? Some of it goes into turning the axle. A lot of it goes into generating heat. So the input power turns into the output power plus the heat that's generated every second. That's why it's more. It's important you understand. Input's always going to be more because it includes the energy that you're losing in terms of heat due to friction. Okay, so listen, your workbook made a mistake. It doesn't include this factor, so make sure you do. You need to include multiplication by 100%. Efficiency is not a decimal, it's a percentage. Okay? One more point here before we go on to calculation. Efficiency is always less than 100%. You're never going to have a 100% motor. You can get close to it with the electric motors, like the Tesla motors. It's true, they're pretty efficient. But you're not going to get 100%. Just finish this. Always less than 100%. Why is the efficiency less than 100% in all working motors, in all mechanisms? Why would that be? Why not 100? 100 would mean all of your original energy goes into turning the wheels. What do you know about spinning parts, moving parts? Very good. And friction generates, yeah, that's why. That's why you never get 100% efficiency, because there's always some energy lost in the form of heat. 100% would mean no energy lost. All of the energy of the gasoline goes into spinning the tires. No heat loss. Yeah? No. It's a con job. That's pretty bad. I know some people are selling stuff. I got sucker. I'm just kidding. No, I don't. I tell you this. Tesla did some experiments. He said, and they made fun of him. Because he was the one that came up with the engine that they're using in the actual Tesla cars, right? It's called an induction motor. It's very efficient, high torque. less friction, right? Anyways, he came up with the idea. He had all sorts of ideas. One of the ideas is he said you could actually get energy from the atmosphere, and they made fun of him. They said that's not true. It's all bogus. They're actually doing it now. But the problem with that is you've got to set up huge collectors, but it is doable. So Tesla was interested, but that's not free energy. That's energy that exists because of the cosmic rays. So it's generated from the sun. What? Oh, you were looking at my tabs. Where does it say? Oh, I was looking at stuff. That was just me and my conspiracy ideas. Forget it. Anti-grav. There actually were some experiments done in the later part of the 20th century where some people claim they got anti-grav. I don't know. I just want to know whether there's anything to it. So far, I don't see it, but who knows? Just one more after this on circuits. After we finish this, circuits. Okay, so 5 more minutes. Try page 168 out. Look at the sample problem, and then you could try page 169, 1 to 3. So do 169, 1 to 3. Stop, record. Well, I got most of